Now let's look at slope and algebra. And at this point, I want to also toss in here proportionality. In particular, we're going to look at direct proportionality. And so in terms of algebra, when we think about a slope, we think about, say, probably most people would think about something like this: y equals mx plus b, where this is telling us a relationship between two numbers x and y. Now we're going to get to this more complex relationship in the next module, but we'll mention it just a little bit here, in that the m is what we call our slope, or the rate of change of y with respect to x there. And then b is a constant that is what we call the y-intercept. And graphically, from this algebra, we would see the line get shifted up or down. We're not ready for that yet. So what we want to do is we want to nix this b. So we want to just talk about y equals mx. Okay, so we'll concentrate on slope here. So what we have is that y is equal to some constant times x. So here m is a constant. Now, if we restrict m to be a positive number, then what we say is y is directly proportional to x. Okay, means, so I'm going to say, this is what it means when we say that. It means, simply algebraically speaking, y equals k times x, where k is greater than 0. I'm not aware of when people would make it a negative number. Just when you start talking direct proportionality. Certainly with slope, it can be a negative number, but with when you start talking direct proportionality, that constant typically is a positive number. So where k is greater than 0 and k is called, now in this case it's not called the slope, it works the same way, it's the same kind of number, it is the rate of change of y with respect to x, but it's called the constant of proportionality. So what you see is when you start talking about direct proportionality, it's really just a special case of this idea of slope. So we could have y equals mx, where m is any constant, including 0. So we could have a slope of 0, and then we have this idea of the constant here of proportionality. Now, so what we need to do is be able to translate between our algebra and our other languages, our graphical and tabular languages. So here, we want to translate from algebra, and we're going to go to tabular first, just because what we can do here, and you all have done this sort of thing, is we're going to make a table, and there's x, and usually these are called t-tables, and then we're going to let y equal, now let's pick a slope, maybe like -3x, like that. And so what we see is I can start picking values of x, and often what we did, you know, I'll start with -2, and when x is -2, -2 times -3 is 6. Then I could put in -1. When I put in -1 into there, I'll get a +3, and then 0 gives me 0, and 1 gives me 3, because, -3, because 1 times -3 is -3. And if I put in 2, I'll get -6. And we can check that that -3 really does, in the algebra, really does mean this idea of slope, because, well, I can check that pair, and when I check that pair, I have, now you got to be careful here, I'm going to do 3 minus 6 over, now the 3 goes with the -1, minus a -2. Now it probably would have been a little easier to use some of these, but no matter what, I kind of had to deal with negative numbers. And so my slope here is, well, 3 minus 6 is -3, and -1 minus a -2, that's -1 plus 2, and so I get -3 over -1 plus 2 is 1. And so I get a -3. And so we see that, yes, that's why back here we call it y equal mx like that, because what we find out is if we put these numbers that satisfy that relationship into a table and check its slope, we get that number, -3. That, you know, so, oh, that's our translation. So if I see, you know, y equals -3x, now I know if I were to make a table of numbers that satisfied that, if I checked any pair of xy, or, you know, any two xy pairs and check their slope, I will get that number right there, -3. Wow, you know, so you see, really, I've just done a translation between the algebra right there and then the tabular right here. And so now we can take that further, in that if I take those points we just made and I make a graph with those, so there's -1, -2, 1, 2 for the x, and we need to go all the way, you know, we'll go 3 there, 6 there, -3, -6, like that. Then if we plot those points, well, we had a -2 and a 6, we had a -1 and a 3, we had a 0 and a 0, we had a 1 and a -3, and we had a 2 and a -6. And you see, oh yeah, that's a straight line, and we know that straight lines have this notion of slope. And so we took the algebra, so we had that algebra, we translated it to the tabular form, and then we translated it to graphical form, and we see we've got a straight line. Now, in particular, the way I know I've got this relationship is 0, 0 always makes that work. No matter what, you know, if I had y equals 322x, 0 equals 0, if I put 0 in for x and y. So 0, 0 always makes this type of equation, y equal mx or y equal kx in the case of proportionality, it always makes those work. And so what I now know is I always get a line that goes through the origin of my Cartesian coordinate system. And so you see now I have a way to sort of translate between algebra and the graphical, in that if I see something like this, right away I know that if that's x, that's y, then y equals some m times x. And then if I could look at the graph and actually count, and suppose, that was a 3 and that was a 4, then what I know is m equals 4/3. And so my algebra, I can look at that picture, but then I know my algebra for that picture is y equals 4/3 x. So I've translated from the visual or graphical language to the algebraic language. And this is very, very important to succeed in any sort of algebra-based mathematics. And I would say even some things that aren't quite as algebra-based, but the key is to translate, to think of it as language, and think about translating between these three sort of realms of graphical, algebraic, and tabular. And then a little more than that even, to really solve a problem that you want to solve or somebody else wants you to solve or something like that, well, you also have to translate between English and mathematics, or the mathematical languages. So somebody may state a problem in English like, oh, well, I have 3 oranges and 2 apples. How many pieces of fruit do I have? Well, there's an English statement, but now I could change that to an algebraic sort of statement. Now there's no x involved here. Or I guess I could say 3 plus 2 equals x. I want to know I've got 3 oranges and 2 apples. I use that because I'm a rebel and, nobody's supposed to add apples and oranges, but there I just did it. So 3 plus 2 is x. That's an algebraic sort of thing. But now, I know that, oh, that's 5. 3 plus 2 equals 5. So I had my English statement of, well, I had 3 apples and 3 oranges and 2 apples. I wanted to add those up and find out how many pieces of fruit. Well, I can write that mathematically in algebra with the 3 plus 2 equals x. So more complicated problems takes more complicated mathematics, and you get very confused very quickly if you don't know how to translate between the various languages. And so you really want to think about it that way. This is a matter of translation. And again, this is slope, but it's also this idea of the constant of proportionality where two things are directly proportional. We've got y equals kx is all that it means. And really the only difference is if I'm talking about things that are directly proportional, then that slope or constant of proportionality is, at least as far as I know, I'm going to assume it's positive. It's a positive number. Whereas if you're just talking about a straight line in general, and it has some slope or some rate of change of y with respect to x, well, that rate of change could be negative. So in other words, I could drop the y value as x increases. And so it's just a slope is a more general term than directly proportional or constant of proportionality. So if I'm looking at proportionality, that is not as general as slope, but is very similar. And of course, slope, again, as we looked at right at the beginning, I could have added that b on there, and so we can see there that I can even talk about slope, a positive slope, and not have things be proportional, because if I added a constant on there, it doesn't fit this definition down here. Okay, so we were just looking at lines in a graphical sense. We're just looking at lines that go through the origin. And in the case of proportionality, we just happen to know those lines have a positive slope. Okay, so instead of going down as they go to the right, like this one does, they would go up, okay, and look like that. So there, I think I've said about all I can really say right at this moment about slope.